So,
Yeah, we are live.
so welcome everyone. This is Agarwala, who's going to chair the session, the post tea session in the morning. And without further ado, we will have Aditi Day to give the first talk on quantum thermal machines.
Okay.
The talk is for 30 minutes.
Yeah, thank you, Sadiq, and thank you, organizers, for giving me this opportunity to speak here. So I share the screen.
Yes, please go ahead.
Yeah. So can you see the screen?
Yes, Aditi.
Yeah.
Okay, so as already Sadiq said, I will be talking about quantum thermal machines. And the work is based on few of our recent papers, which are in archive, as well as some are published recently. And the work was done with the collaborations with three of my students, Ganesh, Srijan, Tonay. Titash was also my student, but now in Italy for postdoc. Amit is a faculty at IIT Palakkad. Shiladitya is in abroad. So the outline of my talk is the following. First, I will try to motivate ourselves that why should we study thermal machines. Thermal machines means I'm talking about quantum heat engines, quantum batteries, quantum refrigerators. I will also try to argue that actually these studies are important to build up the field called quantum thermodynamics, which are not yet quite settled or developed. Then I will talk about quantum batteries, where I will present some of our works, and I will show you that these batteries are robust against impurities or against decoherence. I will also, if I get time, I will also mention the very recent work where we have shown that the battery's performance can be enhanced by using, if you increase the dimension of the system. Then finally, I will talk about a design of a quantum refrigerator and show that they are also robust against disorder or impurities. And finally, I summarize. So let's start with some motivational slides telling that what are the thermal machines. So we know the thermodynamics, which we learn in our usually college and universities, that the main goal in this field is to design heat engine and thermodynamic processes, and it's a very well developed subject. For example, one of the prominent work include the almost 200 years back, where Carnot gives the upper limit on the efficiency during heat into work. Now, so this subject or this field, I will call the classical thermodynamics, where a classical thermodynamic machine consists of a working medium and which is enclosed in a cylinder with a movable piston. Now, with the miniaturizations of devices, it is important to formulate fundamental thermodynamical principles and bounds in the regime which is valid in a microscopic level, in a quantum levels. And we understand that these bounds or the principles may differ from classical ones. But the hope is that they will converge. The bounds will be such that they will converge in a macroscopic limit. And so there are many works in over the last few years. So one of the first works is almost 60 years back, where it was shown that if you use 3-level measures as heat engines, then it will be actually perform something different than the conventional heat engines. So after the initial work, several models, several thermal machines were proposed based on quantum mechanics, quantum mechanical systems like harmonic oscillators, spin chains, molecular devices, and 3-level systems, etc. And in this respect, I just want to mention the beautiful book by Mehlar and others, this about quantum thermodynamics. So, for example, there is a recent work by Mehlar and his group that actually proposed a machine which is made of 3 spin and these are situated linearly. And one of the spin is attached to the hot bath, another is attached to the cold bath. And they show that this actually is an efficient quantum engine, and the performance depends on the temperature difference of the bath or the energy difference of the system. There are also a lot of debates in these directions. For example, it was shown that there is a violation of second law of thermodynamics, or the engines have efficiency which is more than Carnot's efficiency. But both of them are resolved in a sense that it was shown that none of them are true or hold, because this can be solved, for example, by using quantum memory. So as I said, there are several works in specifically last 20 years or so. I will be concentrating on two work. One is on quantum batteries and another is on quantum refrigerator. So let's start. What are batteries? As we know, they are very useful devices, and the batteries that we use, I call again that as classical battery. And these classical batteries are such that they are electrochemical cells with external connections for powering electrical devices. It converts chemical energy to electrical energy, and this energy can be extracted whenever needed. The question that we ask, like other quantum technologies or quantum devices that we want to build, can quantum mechanical system help in storing energy and as well as extracting energy? Now, in this directions, one of the proposal is by Alichki and Fanes in 2013. So they show that if you take a d-dimensional quantum system with non-degenerate energy levels, then this can act as quantum battery. And then what can be extracted reversibly if we apply entangling unitary operator. And as we know, that unitary operations are cyclic. And so if the energy that we can store, we can also extract it. The same amount of energy can be extracted via same unitary or the inverse of the unitary operations. I will actually discuss this point in detail, because I will show that when we talk about decoherence, then the things are pretty complicated, and then we cannot actually this reversibility will no more true. So the two prominent designs of quantum batteries are developed over the years. One is the first one, where there are array of two-dimensional systems, which are more closely related to Alichki's proposal, where the charging are done via global unitary operation. So as schematically shown, and this is with a cavity, this was a proposal. And there is another one which were proposed, where there is a there are a series of say spin-up particles, and the initial state of the battery is the entangling one, and then the charging are done by a local unitary operator. I'm not introducing entanglement here, because it's not. I mean, that entangle in initial state is not so important in this in the performance of the battery, or rather it is not clear whether entanglement will be helpful for enhancing the power of the battery and so on. Rather, the initial state is the ground or thermal state of an interacting Hamiltonian is the important point. And so this I will elaborate, and actually I will talk about more about design 2. So where the initial state is the thermal or ground state of the interacting Hamiltonian, and the charging are done by local unitary operator. There are two proposals, one initially by Kavan, Modi, Pollock in 2018, and next one is by us. So there is a difference between these two, but I will mainly highlight on our proposal. So why we use quantum spin chains to design a quantum battery? As we know that they can ask or they can answer several important questions in or fundamental questions in physics, like quantum phase transitions, out of equilibrium properties, thermal properties, etc. At the same time, we know that they are the potential candidates for realizing quantum technologies, which include quantum computer, quantum state transmissions, which are also required to build quantum computer, and so on. And apart from that, it is also important that they can be realized in laboratories. For example, by using photons, now the spin models are shown to be realized, say the ground state of the Heisenberg or Ising spin chain. We know that it can be realized by trapped ions, where they can create a very long-lived multipartite entangled states by, for example, by polar molecules and so on. So these models that we plan to design can be realized in laboratories is additional motivation to build it. Now, this is the work that I'm going to present. So this is in this paper, we show that if you choose interacting spin half model, which can act as a quantum battery. So specifically, the ground state or the thermal state of a spin half model can act as a initial state of the battery. And this is the Hamiltonian that we have chosen. This is a well-known XYZ model. And so this delta is a coupling in the Z direction, J is a coupling in the XY, and gamma is anisotropy. And there is also a magnetic field in the Z direction. And the initial state of H0 can act as an initial state of the battery. Then we use local magnetic field to charge the battery. So then the total work output, so this is how we characterize the performance of the battery. So total work output of the battery can be quantified by like that, which is a difference between the output or the resulting state with the initial state, and the average power will be after maximizing the work with respect to time. What if I choose this XYZ model, the ground state of this model as a battery, initial state of the battery, and we use local charging field, which is in the X direction, then we can clearly show that there is a regime where the interaction help to enhance the power of the battery. And this is this. This plot is for the XY model with different anisotropy parameter, and delta is 0. But the similar situation happens when you also introduce delta, and so that means when XYZ model also act equally well for quantum battery. Let's now let's now discuss that how robust this model is against impurities. So what we did, that one of the interaction strengths now depends on site. So either we choose delta J depends on site, or JJ, that is the interaction strength of the in the XY plane, depends on site. And so these are the disordered system. So how will we calculate power in this system? So we perform quench averaging. So we first compute the power of the battery for each realizations with randomly distributed interaction strength, and then we take the average over all realization. Now this randomly distributed interaction strength, this randomness we get realized by choosing Gaussian distribution. So for example, if we choose delta J to be random, then delta J are chosen from a Gaussian distribution with mean delta and standard deviation sigma delta. And here, for example, we have chosen the mean to be 1 and gamma, the anisotropy 0.4. And the x-axis is the interaction strength J, where there is no disorder. And sigma delta actually quantifies the strength of disorder. So when sigma delta equal to 0, that means it is there is no disorder. It's an ordered system. This is the blue curve. And you see that when we actually increase the disorder strength, then we get more enhanced power. And this was already, I mean, this is we see for the power, this quench average power. But we know that this enhancement can happen in the introduction of disorder. Although typically we believe that disorder should decrease the performance of the quantum devices, but it is already known that, for example, magnetizations or the entanglement can be enhanced in the introduction of disorder. And we also report that even in a device like quantum battery, where the performance can be enhanced by introducing disorder in the system. Now I move where we have a decoherence in the system. So here we consider again the ground state as the XY model of ground state of the XY model as a initial state of the battery. And now this quantum battery is attached to local bosonic baths. So, and these act as an absorption channel. So local bosonic baths are responsible for supplying energy to the system, as well as after supplying the energy, we stop that and we again attach to another set of local bosonic bath from where we actually extract the energy. And these baths, the blue ones, for example, they actually act as a dissipation of the channel. And moreover, each spin of the quantum battery can be exposed in dephasing noise, which can be phase flip or bit flip noise. And then no more the dynamics are dictated by the unitary dynamics, but you have to consider the master equation. So this is the master equations that we consider, where the Lindblad operators will be like that, which I'm not going into detail. So you have to solve this to find out the steady state or the transient regime, the performance of quantum battery. And in this case, the figure of merit also changes, because here we have to consider ergotropy, which is defined like that. I'm not going into details, but we understand that this is a different regime than the one that I have described via unitary dynamics. Now here we prove analytically that in transient regime, both in presence of beat flip and phase flip noise, the transverse binding model-based quantum battery is, the performance is better than the situations or than the battery which is without the influence of noise. So noise helps again in the performance, but this is only in the transient regime. And here the noise is Markovian. Now here also there is a kind of trade-off, like in case of Markovian regime, we only can show that in the transient regime noise helps, but in the non-Markovian regime, there we can show that the performance actually of the battery can be enhanced both a transient as well as steady state regime by introducing noise in the system. And this is the ohmic spectral density we consider for non-Markovian case. So finally, I just spin half particles. So by qubit, so interacting spin half systems act as a battery. And now we ask the question, what about spin J? And now with the increase of dimension, typically we believe that there is a loss of quantum nature. And so the performance can be diminished. So what is the expectation is like that, but there are results, like there are quantum devices that has been built where it was shown that actually higher dimensional systems help. And this is from quantum cryptography to quantum switch and other quantum communication devices. And indeed, if you take now again the XY model, but now these A's are no more the Pauli spin operator, but the higher dimensional spin operator. And you charge similarly with this is another higher dimensional spin operator. Then we show analytically that the initial state of the battery, if it is the ground state of spin 1 transverse XX model, then the power is more or higher than the XX model consisting of spin-up particle. And this was true only when the interaction strength between the sites are weak. And this figure actually demonstrates that, because you see that the red one is for spin-up particles. On the other hand, the other curves are for different spins. And say, for example, green is with J5/2. And you see that when the interaction strength is weak, because the x-axis is the interaction strength, y-axis is the power, maximum power. And we see that when the weak, in presence of weak interaction strength, dimensional advantage can be seen. And so we get a higher power. We can extract higher power, and we can also deposit higher power. Here I talk only about the unitary dynamics. So the deposit of energy as well as extraction is same. This is so this advantage persists also for other spin models, not only for XY model. So this I will not discuss. This is a very recent work. I just want to mention that up to now, again, we talk about the individual system, which is fixed at space. So each of them can be distinguished from others. And we show that we can go beyond that. We can model quantum battery with indistinguishable subsystems. And this is actually based on the cold atom system, which can be realized in optical lattices. And the interesting part is that this battery has a kind of, the power depends whether you build the battery by using fermionic system or the bosonic one. Finally, I will just briefly mention about the design of quantum refrigerator. And as we know, that the main goal of the refrigerator is to decrease the temperature. And the questions that I want to ask, whether there is a fundamental limit to the size. And also, does quantum mechanics system help? And indeed, it is true, as shown in this 2010 PRL paper by Linden, Popescu, and others, that if you can build a self-contained refrigerator by using quantum particles, quantum spin half or high dimensional system. And here also we use a quantum spin model as a refrigerator. This is the Hamiltonian, and this spin, each spin is connected to the bath. And this is the harmonic bath or the bosonic bath, and this is the spin bath interaction. Now, the initial state of the refrigerator when the interaction is turned off, and then again we actually have to consider, because since these are related to the bath, so we have to solve the master equations, and then we have to characterize the performance by introducing something called heat current or the temperature. Now here the local temperature is also another important questions in this field, how to define local temperature in this scenario. So for example, if you think that the initial state of the refrigerator is like that, and so the initial temperature is Ti0, now you evolve the system, and you want to see, say, the rho IT at, so this is at ith side, the evolved state. And then the temperature at time t can be found to be this. And if we found that the temperature at steady state is lower than the temperature of the initial state, then we call that the steady state cooling is achieved. And indeed, by using quantum spin model, we show that temperature decreases of the first spin. And so it behaves like a proper refrigerator. You can increase the number of spins to be 2 to 3. Again, you find that the temperature decreases. And at the same time, we know the heat current should increase, and this is clearly shown. And again, we can choose that the interaction strength depend on site. So we introduce disorder into the system. And the Gaussian distribution, the interaction strength are chosen from Gaussian distribution with mean J and standard deviation. And we find that again, the quenched average temperature shows a similar trend. So you see that it is decreasing. So we can say that this model is robust against impurities. So I summarize that quantum spin models are important to implement quantum technologies. Here I highlight two technologies. One is the design of quantum batteries, and I show that they are robust against impurities. I also have told you that if you increase the dimension, you actually get enhanced power. I haven't shown, but I really feel that this is an important work, that designing of quantum battery by using ultra cold atoms, which can be realized nowadays in laboratories easily. And then I show that there is a self-contained quantum refrigerator can be designed by using quantum spin model, and they are robust against impurities. So this is the current group of mine. So this is mostly my students, and Orgo is a postdoc under the DST project, which many of you know about quantum enabled science and technologies. And this is the entire QIC group. It's a bit old photo, but thank you very much for your attention.
Perfect timing, Aditi. This is absolutely perfect timing. So we have the session open for questions. People can raise their hands. There are some questions in the chat which I can read out.
Yeah.
So the first two questions are kind of pretty similar, which is why noise. Are you reading the chat?
Yeah, I'm reading.
Right.
Okay, so the first two question is quite similar, as you said. So yeah, as I said that it's counterintuitive, okay? And so that's why it's interesting. But we know that when you introduce disorder in the system, so then and you perform the quench averaging, then there is a possibility that you get enhanced performance. And if you follow the literature of disorder system, there is this disorder enhanced order. So you have seen that the magnetization or correlations or entanglement typically also enhanced by introducing disorder for some range. I'm not claiming that it is always increasing, but we find parameter space where one can enhance. So this is the finding that parameter space, which I should have emphasized. That part is important. So it's not true always. So it is only true. You have to find a parameter space where actually the observable that you are considering, if it is in ordered case, is monotonically increasing, you understand that when you choose Gaussian distribution, then and you perform averaging, you actually get enhancement. That also you can understand mathematically. So this is what we got. And then how does quantum phase transitions affect? Yeah, thank you, this question. But one thing I should mention that here we are designing quantum technology for a very small systems like 3, 4, the battery, we can go up to 8, 10, and so on. When we do recurrence, it will be very hard to simulate because we have to do open system dynamics. So really the phase transition doesn't affect so much because, as you know, we have to go to really the thermodynamic limit and so on. So I'm not sure that, we haven't seen that phase transition has any effect. So these are the questions in the chat, but there are some raised hand, I guess.
So I think your spin chain is either in the ordered phase or disordered phase. Does it affect the performance of the battery?
Sorry?
So your spin chains, whether it is in ordered state or in disordered state, does it affect the performance?
Yes. You mean in this you are talking not about a disordered model, but the ordered phase and disordered phase, right? In ordered
like paramagnetic
system,
phase
right?
or ferromagnetic.
If I understood correctly.
Yeah. Yes.
Okay. Yeah. So actually, it's not as you. Okay. So just to tell you why it is not, because you see. If I can come quickly, here. Yeah. So you see that when these are actually entirely kind of paramagnetic phase where we are talking, and even there, you see that right hand side we get the enhancement, and here there is no. This is because we are considering dynamics, and we put the magnetic field in the x direction. Okay. So we want to. Here you can think that you start with a very low J, right? So the dominant part is sigma Z, right? And the spins are trying to go towards X, right? Because I put the charging field in the X direction. And so the power is getting enhanced. You can think in the physically like that. The power means the energy, right? So the energy that the systems are depositing, or it's not really the phase here matters.
Okay. Okay. Thank you.
Aditi, if I may
Yeah.
ask one question. So in
Yeah.
this, towards the end, you showed us, a definition of temperature, which was essentially like a spin temperature for a single qubit. But when you go to 3, 4, that's multiple states, do you really see a thermal distribution, or how does one define a temperature?
Thank you, Rajdeep. This is a very relevant question. And actually, I have an answer because we are just working on that. Okay. So there, it will not be so simple. Okay. So if you actually, we recently find that just to tell you the temperature here, how I did. So suppose instead of spin half, if you go higher dimension, that is you were talking, right? Yeah. So you can show, if you have this kind of model and you increase, say now sigma, this Pauli to the higher spin operators, then the dynamics in the weak coupling limit, it will be still a diagonal state, but it will be say 0, 0, 1, 1, 2, 2 and so on. Okay. So the initial temperature, you can think something Ti0. Then actually you have to somehow introduce the measure, which is called a distance measure, any distance measure between the steady state thermal state and the initial one. Okay. And in that way, you actually minimize. So you can think that at steady state, you want to see that whether that correspond to certain thermal state or not.
Okay. Yeah. I understand.
And then you want to minimize the distance, because that temperature will be your temperature. And you can show that if you actually introduce that way the distance measure to define temperature, in qubit case, this simplified version that I have shown is indeed the case. I mean, they are already minimized. In higher dimension, you cannot do that. And this is exactly the work that I think we may report this month or something. Actually, we got it.
Okay.
Thank
So
you
we'll wait for your new results.
Right.
Yes.
So thank you very much, Aditi. We have to move on very quickly
thanks.
to the next talk by Bijoy Agarwala from IISER Pune.
Okay, so Sadiq, shall I share the screen?
Yes, please.
Okay. Just a second. So you can see my slides, right?
Yeah, but you have to go full screen.
Full screen, yes. Just a second. Yeah, now it's fine.
Perfect.
Okay, just give me a second. Yeah. Okay, so shall I begin?
Yep.
Okay, all right. So first of all, I would like to thank the organizers for the kind invitation and for putting up this wonderful conference. I should also thank right away to Aditi for giving us such a nice introduction on quantum thermal machines, because this talk is also going to be on a similar theme. Okay, so the title of my talk is about universal bounds on fluctuations in thermal machines and its connection to the so-called thermodynamic uncertainty relations. So my talk will be based on essentially this set of papers, where I'll primarily focus on the very first one, which recently got published in PRL. Okay, so here is the plan of the talk. So I'll first give a very brief introduction to the so-called thermodynamic uncertainty relation, which from here on I will refer as TUR. And I will introduce that in the context of quantum transport, and then I will go to the central theme of this sort of talk, which is about bounds on fluctuations. And I will primarily focus on a particular type of thermal machine, which is a continuous thermal machine working in steady state. And I will talk about two specific examples or cases. One in the case when the system is time reversal symmetric, and another case is what happens if the system doesn't follow a time reversal symmetry, let's say in presence of magnetic field. Okay, so let's begin with the what is this thermodynamic uncertainty relation. So I'll be talking about this relation again in the context of steady state. So imagine that you have a system of interest that could be classical or quantum, it doesn't matter. And this system is in contact with two reservoirs. And for the moment, let's just consider electron transport. Okay, so in order to have transport, what I can do is to keep these reservoirs at a different chemical potential, and I can also have different temperatures. So that we essentially call a system which is driven by multiple affinities. So in this case, there are two affinities. One is the chemical potential difference, another is temperature difference. And as a result, I will have multiple currents that will flow in the system. And let's look at what happens in the steady state. So what this TUR tells you is essentially is that it gives you a trade-off relation that involves two quantities. So if you look at this particular relation, which involves the sigma average, which we call the entropy production rate, and I'll come to that, times a quantity which is so-called the relative uncertainty of any particular current that you want to look at. So you have, let's say, charge current. So this quantity is nothing but the fluctuation. So this d alpha is related to the fluctuation of current in the steady state divided by its average current square. So this is nothing but the square of the relative uncertainty. So what this relation tells you is that the relative uncertainty of any individual current that you look at for a system in steady state, that cannot be arbitrary, but rather the product of this relative uncertainty times the entropy production rate is always lower bounded, and this bound is given by 1. Okay, so you cannot minimize relative fluctuation in an arbitrary manner, but rather you have to pay a cost, and that the cost is entropy production rate. And what do you mean by entropy production rate? It's basically related to a system which is driven out of equilibrium. So essentially, entropy production rate you can define as current times the affinities that you have within your system. So essentially, it's a bilinear in the affinities. Okay, so how do you prove this? This result turns out to be universal, and it's valid. A proof requires essentially two ingredients. One is the Onsager reciprocity relation. So this relation is, so I'll be primarily focusing on only in the linear response regime. So when I have, meaning the currents are essentially linear in affinities. So when I have that, then for multi-currents, I essentially have this Onsager matrix. So all I need is a two central property. One is the Onsager reciprocity relations, meaning let's say if you have two currents, the off-diagonal elements of the Onsager matrix are symmetric, and the positive semi-definite property of the Onsager matrix. So once you have these two property, you can very easily show that these bounds pops out naturally, and it's universal. Okay, and when does the equality happens? It happens for the single affinity case, which essentially gives you a Green-Kubo formula. And you can also have for multi-affinity case, but in tight coupling. So I'll come to that at some point. So we have been exploring this relation in other contexts also, and here are some references. So if you're interested, please take a look into it. But today I'll be mostly talking about this relation in the context of engines. So this bound was first given by Udo Seifert in 2015. And later on, this relation was applied in the context of thermal machines. So note that this is one relation which is for systems out of equilibrium, and that has fluctuations. It's a bound on fluctuations. Okay. So what happened is that if you apply this relation in the context of engine, you start to get very nice universal bounds. So for example, you can actually show that you have a system, for example, on the top where you have multi-affinities, multi-currents. So you can talk about an engine, meaning converting one form of current to another. In that case, you can show that this consequence of this uncertainty relation is essentially imply a tighter bound on efficiency and tighter than the standard Carnot bound that we know from macroscopic thermodynamics. So here, this new bound is now incorporating the underlying fluctuations. Okay, so that is one central message that you get out of this bound, as well as you can also bound the power output in terms of as an outcome of this relation. So you just take these relations, apply, and you can get this output power. And you can actually recast these bounds in terms of different fluctuations, because remember, there are multiple currents, and for each current, you can actually write down this TUR, and as a result, you can actually get multiple bounds on this power, which at this point looks very independent to each other. Okay, but what we'll show is that they are not really independent, but rather follow a strong, strict hierarchy. So this entire thing actually has related to TUR has taken over, and it has been applied in various contexts. But today, what I'm going to talk about is that how do we understand this bounds on fluctuations in the context of machines in more detail. Okay, so let's start. So this work is recently published in PRL. So most of the details you can find there. So I'll go over very briefly the central result of this work. So what we'll focus on essentially two affinity problems. So we'll simplify our life and we'll just focus on two affinity. So think about a thermoelectric kind of transport or a machine where you have chemical potential difference and temperature difference. And what is the central result? The central result is essentially here. We look at a particular quantity which we now call eta 2, which is nothing but ratio of two quantities. It's a output fluctuation over input fluctuation. Okay, and it will be clear as we go along. So just like average efficiency that we look at, which is nothing but the average work or average power by average heat, we are essentially looking at the next order. We are looking at the ratio of the fluctuations of output over input, and it turns out that this not only has an upper bound which is dictated by eta c square or eta c square naught, it also has a lower bound which is dictated by which is basically has both upper and lower bound dictated by Carnot efficiency and average efficiency square. Okay, so this is the central result that we receive in this, and let's look at how we essentially arrive to that result. So I mentioned it's a two affinity problem, and we are always going to work in the linear response. So you can have these two currents and you can write in terms of the affinities to the linear order. And as a result, what you get is a Onsager coefficient Lij. Okay, and if you have a time reversal system, then Lij is nothing but Lji. The off diagonal elements are essentially same for I not equal to j. So now, what we are interested, since we are interested in fluctuation, let's right away construct the quantity which is relative uncertainty of individual current. Okay, which is nothing but the ratio of the fluctuation over the current square. So this is square of the relative uncertainty. And what we can look at is construct a quantity which is a ratio of relative uncertainty of these two currents. Remember, we are talking two affinities, so we have two currents. And so this Q is an important quantity, which is the ratio of the two currents, the relative uncertainty of two currents, and we can write this thing in the linear response. Okay, so here is what you get. So that is very simple. So far it's very general. The only approximation is that it's a linear response. So then if you massage this expression, you can rewrite this quantity Q as a sum of 1 plus something. Okay, now this something turns out to be very interesting. If you open up, if you sort of write this, you actually get this term as a product of two terms. Okay, now right away you can identify the second term, which is nothing but the negative of the determinant of a Onsager matrix, and that always have a definite sign. You see, once we have a second law, which essentially says that the entropy production rate has to be finite, has to be non-negative, that immediately implies that the determinant of Onsager matrix has to be positive or non-negative. And as a result, this quantity L12 square minus L11 L22 has a definite sign, which is negative. So that is great. But what about the first term? The first term in general doesn't have any definite sign. But the moment you impose the condition that let's have this non-equilibrium setup working as a machine, or let's say as a thermal engine, then you can show that this quantity, the first term, is also always negative, non-positive. And as a result, this product of these two terms becomes positive, and you can actually have Q to be greater than equal to 1. Okay, and how do you show that this is always negative? Is very simple. So remember, that happens only when you work when you impose the condition that this is a machine. So as I said, there are two currents. So let's just consider now that I1 as input current and I2 as output current. So now these currents have definite directions. When you talk about a machine, I want something to absorb and I want to extract something. So there is a perfect directionality of these currents that flows within the system, and I need to impose those conditions. So my convention is that the current flowing into the system is always positive. So if I consider I1 to be input, then I impose the condition that I1 A1 has to be greater than 0, because I am basically, so that's the current that I'm taking into the system, and that gives me an inequality which is of this form. And I want to extract the 2 because that is my output current, and that leads to another condition in terms of Onsager coefficients and bias. If you combine these two conditions, which ensures that your system is working as a machine, you essentially get this relation, this particular inequality. And as a result, the central result you get is that this ratio of this relative uncertainty of output over input, remember now 2 is output and 1 is input. So relative uncertainty of output is always larger than relative uncertainty of input when your system or setup works as a machine. Okay, and as a result, what you can immediately show, the quantity that I showed you, TUR, which I initially said that for individual currents, there seems to be no relations between these currents. But when a setup working as a machine, you always will have the TUR for output current to be always large. You always multiply by entropy production rate, which is positive, and your proof goes through. So that's the central message. But then out of that, you also get a very interesting result, which is essentially now if you construct this ratio of the fluctuations, which I call eta 2, it gets a lower bound and it gets determined by the average efficiency square. And you can also find an upper bound on this ratio of fluctuations, which is nothing but eta c square. So here I have written it in a scaled version, but if you apply for a thermal machine, it becomes eta c square. So the central bound, the central result that you get is this quantity eta 2 receives, which is the ratio of fluctuations, receives a lower bound and an upper bound. And in fact, interestingly, if you take a square root of this equation, this inequality, you actually see that eta average is less than eta c, which is great, but you also get a tighter bound, which is square root of eta 2. So you're now getting, by introducing fluctuations in your study, you are essentially now getting a much tighter bound compared to what we know from macroscopic thermodynamics, which is Carnot. Okay, so this result is not only valid for heat engines. You can also, so in general, it's actually valid for thermal machines, meaning you can have these relations for heat engine as well as refrigerator or pump, and you can always have you just have to identify what is your output and what is your input, and you will always see that the relative uncertainty of output is always going to be greater than relative uncertainty of input. So that is one of the central result. So just to show as an example, what we can actually do is to consider a non-interacting charge transport setup, which is connected by two baths having two affinities, and this problem can be exactly solved. Remember, we need both current as well as fluctuations. So typically these are difficult calculations, but at least for non-interacting problems, these are not so difficult. So this is a non-interacting problem. So here the average current is simply the Landauer formula, and similarly you can actually get the fluctuation also, and this is the generating function that I have written down, and it's famously known as the Levitov-Lesovic formula for non-interacting electrons. And here is a result to verify what I showed, that eta 2, this plot where I'm looking at a contour, sort of a two-dimensional plot as a function of the gamma, which is system bath coupling, and here is a epsilon d, which is a dot energy. So I'm just considering a single dot which is sandwiched between two baths, and charge transport is happening, and I'm just looking at what happens to eta 2 minus eta average square. So this you see is always positive. So this verifies the lower bound. And on the right side, right panel, you see the verification of an upper bound. So this is in the linear response, and we have a proof. So this essentially verifies that. But you can immediately ask what happens beyond linear response, and that has not yet resolved. All we were able to do, of course, is to take this expression and look at what happens numerically. And what we found, interestingly, is that this bound still holds, but there is no proof yet. So that's an open question. But at least in this plot, we see, and we did a quite high level of numerical simulation over large parameter space, and we see validity of this relation even beyond linear response, but there is no proof yet. Okay, so that was the first example. The other example, as I mentioned, that you can look at for engine as well as refrigerator or pump. One of the things that you can, what Aditi also was talking about, was refrigerator. So here is one example of an absorption refrigerator. What it essentially does is that you have a system coupled to, let's say, three terminals, hot, cold, and work terminal, where the work terminal has the highest temperature, and the task that you have is essentially to extract energy current or extract energy from the cold terminal and pass it to the hot by taking help from the work. Okay, so this is this way you actually realize a refrigerator, and our formalism essentially goes through here as well in the linear response. And since in this case the output is cold current and the input is work current, you can actually show that the relative uncertainty of cold is always greater than relative uncertainty of W. And as a result, you essentially get a similar bound also in the refrigerator regime, which in this case we showed for a 4-level system instead of a 3-level system, because in 3-level it becomes a very trivial result, which all equality signs. So if you have a 4-level, you at least go beyond equality and you get some nice essential results. So here you look at this epsilon 2, which is this field red line, and that has that essentially fits between the upper bound, which is this dotted, and the lower one, which is epsilon average square, which is this blue line. So that essentially verifies again the study. But we can actually say more about absorption refrigerator, because you see there are now 3 terminals. So we are talking about cold and work. You can also say what happens for the hot terminal. And in fact, what turns out that because you have this directionality fixed for each current when this setup working as a refrigerator, you essentially not only have a bound involving cold and work, which is output and input, you essentially have a strict hierarchy between all this relative uncertainty involving all 3 terminals. So you essentially have much more general result, which is involving cold relative uncertainty is higher than hot, the higher than work. So initially I showed you only cold and W, but in fact in the refrigerator condition, or in the condition when all directions of the currents are fixed, you have this very nice hierarchy. And as a result, the bound that I initially showed you that you get following from the TURs for individual current, which was initially thought to be all independent, in fact they receive a hierarchy because of this relation. So as a consequence, here is the result that the output power also receives a hierarchy because of this hierarchy that we showed. And here is once again a numerical result for a 4-level absorption refrigerator, where you can write down a master equation for the system population, look at the rate matrix, calculate the current and fluctuation. So I'm not getting into the details, but here is the left panel is essentially showing you the hierarchy in the bounds for the power, and you can see that how this hierarchy is essentially getting followed here. And we also have the bound for the average efficiency for the refrigerator. And in this case, you have 2 bounds, right? One you get from the TUR and another from this relative uncertainty hierarchy. And what one we can show is actually the bound obtained from relative uncertainty is always tighter than the one that you obtain from TUR, which is also clear from here. So this blue one is the average efficiency. The bound that we get from hierarchy of relative uncertainty is the red line, and this epsilon C is what you get from the TUR. So this is a much stricter, sort of a stronger bound, and that intuitively is because you are now on top of TUR. What you have is the directionality that you are fixing for the currents. Okay, so far this was all about what happens if your system is having time reversal symmetry. So remember, we are working in the linear response, and we assume that the off-diagonal elements of the Onsager matrix are same. So Lij equal to Lji. But a general, a very natural question that immediately one can raise is that what happens if we break the symmetry? Okay, and that is that's something that we recently just finished working on, and we put up on archive. So here is a central central result that we got in this work. So once again, broken time reversal symmetry imply off diagonals are not same, but what you have is the generalized relation, which is Onsager-Casimir relation, which says that Lij equal to Lji bar. Now, what does the bar means? So if you have a forward process, so imagine you have a transport happening in presence of magnetic field, you break the time reversal symmetry. So Lij, if you have for a particular direction of magnetic field, if you compute the current, the bar indicates that you just reverse the magnetic field and look at the current. In that case, you will see, so Lij, if it is with respect to phi, Lji bar is with respect to minus phi, and that will be restored, and that is what is known as Onsager-Casimir relation. So what happens now? How do we take care of these bounds? I mean, the question is that does these bounds hold in presence of magnetic field or not? So here what you have to do is to actually take into account 2 separate processes. I mean, this forward process as well as the reverse process. So the forward process, you can similarly write the current in terms of Onsager coefficients and bias in the linear response. And similarly, the reverse process is also going to be this, which indicates by a bar. Okay, and now these 2 response coefficients are related by Onsager-Casimir relation. Okay, and what happens to the positivity property of the Onsager matrix? Well, you have the entropy production rate, and that has to be always non-negative because that's the second law. And as a result, you get a generalized relation version of the constraint, generalized constraint on the Onsager elements, which is that the diagonals are always positive. That is fine. And you have now the symmetric part of the determinant of the symmetric part of the Onsager matrix has to be positive, right? And if you have L12 equal to L21, then of course you get back to what we discussed before. So this is the setup. Now what happens is the following. The central message is the following, that you get back all the bounds that we discussed in the time reversal case if you just change the definition of relative uncertainty. So now the relative uncertainty that you have to incorporate both the forward and backward process fluctuation as well as the average. So the relative uncertainty should involve both the forward and the reverse process. Remember earlier it was just di by I average square, but now you have the sum of a relative fluctuation of both forward and reverse, as well as the sum of currents of both forward and backward. So if you construct that way, essentially you get back everything in terms of the symmetric component of the Onsager matrix, and that has a very nice constraint coming from the determinant, and as a result you get back the entire sort of the bounds. And not only that, you now remember these hierarchies that I'm showing is always valid when the setup works as a machine. So you have to impose the same machine condition. So whether if it is an engine, you have to impose the engine condition both in the forward and the reverse, or if it is working as a refrigerator, you have to impose condition in both the refrigerator condition in both forward and reverse. So if you do that, you follow the similar step, you can actually show once again the relative uncertainty of output is always greater than relative uncertainty of input. And as a result, you once again get a very similar looking bound, where very interestingly, the upper bound is always eta c squared. The upper bound doesn't, just like the average efficiency of an engine is always bounded by Carnot, no matter what you do. Similarly here, eta 2 seems to be always upper bounded no matter what you do by eta c square. But it's not a trivial sort of a result. And there is a lower bound, which is that you have to now modify. So that is a generalized efficiency, which involves the output of both forward and reversed divided by the input current of both forward and reversed. And similarly, you can, as a result, show that the TUR also receives a hierarchy when the setup works as a machine. So I just, yeah.
You have 5 minutes.
Yeah, so I'll just, another 2 slides. So maybe another 2 minutes I'll be done. Okay, so here is the result for one of the setup. So here we considered a 3-terminal triple quantum dot setup, which indicated by these 3 sites, and you have a magnetic field in it. So this tunneling elements receives a phase factor determined by this phi. So now in order to, so this, if it is a non-interacting setup, it still doesn't, it has this phase rigidity, and as a result, you cannot break the Onsager reciprocity relation, meaning it will still have L12 equal to L21. But if you take one of the terminal as a probe, meaning that you impose the condition that the net current flowing from the probe through the dot is 0, then you can actually break the reciprocity. You can break L12 equal to L21 symmetry, and as a result, and then you can basically study the system. And here I'm showing the results for the currents, which looks different in the forward and backward. So that essentially indicates that you have broken the standard time reversal symmetry, L12 equal to L21. And this is the first lower plot, essentially showing you that the relative uncertainty of the cold of the charge current is larger than the relative uncertainty of input current, which is the heat current. So that is about the lower bound. And here is a scatter plot, which is essentially showing that the eta 2 has an upper bound, which is the eta Carnot square. So that is essentially for this model. So with that, I would like to summarize my talk. So what the central message that I pointed out is that if you have a thermal machine, which by definition working as an operational device, which could be an engine or a refrigerator or a pump, then this TUR relations that was thought initially to be independent for different currents, in fact, they are not. In fact, what you can show is that the relative fluctuation of output is always larger than relative uncertainty of input currents. And as a result, you get a very interesting bound on the ratio of fluctuations, which has both lower and upper bound. And upper bound gets dictated by the Carnot efficiency square, and the lower bound is by the average efficiency square. So that was the result for system with time reversal symmetry. However, if you break that time reversal symmetry, you can still generalize the case. And in this case, you have to now consider or define the relative uncertainty by taking into account both the forward and the reverse process. So before I thank everyone for their attention, I just like to highlight that there will be a talk by one of my postdoc, Madhumita, who will be talking about one of this recent result that got published in PRL, which is about looking at subdiffusive phases in clean long-range systems. So if you're interested, please attend the talk. And with that, I would like to thank all of you for your attention. And I would also like to thank my students, Sushant and Sandeepan, who did most of this work. We also collaborate with TS Mahesh Group to understand these relations in NMR setup. So thank you, everyone.
Thank you, Vijay. Are there any questions? I do not see anything in the chat. Does anyone want to ask a question? Okay.
Can I ask a brief question?
Yes,
Hi, Sadik.
Hi.
Hi, Bijoy. So I had a brief question. So the question is, I suppose that some of these fluctuation measures like this of this efficiency, the ultimate aim is to understand how much of an efficient and reliable machine you could make.
Right.
So now I was wondering, this measure you've introduced with this ratio of the fluctuations, there can be some pathological cases where, for example, if I have a fluctuation in the denominator that is really small, so there is very precise heat source, and then it might sort of show as though the engine is very reliable, but you could have like a divergent numerator. So is there some idea of when is this measure particularly useful to in the sense of designing an engine?
Yeah, so I would actually take a slightly, so that's a very good question, but I would actually take a slightly different perspective of this eta 2. You are right. I mean, eta 2 being a ratio, if the denominator is small, then it it gives you a wrong indication probably. But I would actually say the following. If you look at this particular equation, the sigma d2 by I2 square, this particular equation, what it essentially tells you is the following. You want, if you want a reliable machine, you want your work, the power output to be as large as you can, as well as you want a less fluctuation, right, in your power output. But what this essentially, this relation tells you that you can't win. The relative fluctuation of power, which is your output, is always going to be larger than relative fluctuation. So at least in the linear response, that's what it indicates. Maybe in the far from equilibrium, you can violate this bound, and you can probably have the reliability of the machine might become better beyond linear response.
Right.
Yeah. Thanks.
Yeah. Thanks. So we have one more question, but in the interest of time, Arnab, I request you to take your question to the breakout room. Okay.
I can do that.
Right. Thank you very much. And we need to move on to the next talk by Victor Mukherjee.
Okay, so I'll stop sharing just a second.
Yes.
Okay. Thanks. Thank you, everyone.
So I am sharing my screen.
Not yet. Okay. Yes.
It is here. Okay. So should I start?
Oh. Yes, please.
Okay, yeah. So thank you, Sadiq, and thank you, the organizers, for organizing this and for inviting me to present our work here. So I'll be talking about fluctuations in collective quantum heat engines. And it was great that Aditi and Bijoy gave a very nice introduction to this whole field. So I'll be talking something about these fluctuations which Bijoy introduced and in something called collective open quantum systems in collective heat engines. So this is, we are doing, it is a work in progress that I'm doing with collaboration with Naufal, my postdoc at IISER Behrampur, and also Sai Vinjanampati in IIT Bombay. Okay, so So motivation, when we talk about heat engines, whether it is classical or quantum, we know that this output of heat engines, most of the focus till now has been on this mean work output, mean efficiency. But also there is this thing about how reliable are these heat engines, and that depends on the fluctuations, the variance of output. So what we'll be asking is if collective effects can make quantum heat engines more reliable. And what I mean by collective effects, I will discuss in the next slides. And also, what about thermodynamic uncertainty relations? So this I'll be showing what I mean by this thermodynamic uncertainty relation also in the next slides. Okay. So first is these collective effects in open quantum systems. So what I mean is, say when we talk about an open quantum system, it is basically a system which is coupled to some dissipative path. Now the coupling can be in two different ways. Say we are talking about a many-body quantum system, say, or many particles, and say the particles, they are not interacting. And the way it can be dissipative is that each particle is coupled to its own local thermal path. And there is an excitation which is traveling between the bath and the system, so that the excitation is not really shared by the different particles. So this is like an independent setup in which each setup is independent to the next one. On the other hand, we can also take something like a collective coupling in which there is a single bath which is coupled to all the spins collectively, all the particles. So that when there is an excitation traveling from the bath to the whole system, that excitation can be shared by all the particles together. And this sharing of the excitation can cause correlations, non-trivial correlations between the particles. So this by collective, I mean a setup like this. And this can be also experimentally realized, for example, by atoms in a cavity, in which there can be some electromagnetic wave, which is exchanging excitation with all the particles. So the question is how the thermodynamics, how the reliability of engines, these fluctuations depend on this independent or the collective coupling. And if we want to make a heat engine, a thermal machine with a many-body system, which kind of coupling is better? Which kind of coupling gives us a better thermal machine? So mathematically, I mean, this Hamiltonian of this collective and independent can be shown like this. For example, if say there are n number of particles, the index given by r, the independent can be something like this, in which there is a frequency that, say we are talking about a two-level system, say, but it can be generalized to even a multi-level system. So this omega, say, is the energy gap for each particle, and then each particle is coupled to the bath with a bath operator Br, and this is the bath Hamiltonian. In case of collective coupling, we have a similar Hamiltonian. The difference is now this it is all coupled to say a single bath, and so the bath cannot distinguish between the different particles. That is the crucial thing, that the bath cannot distinguish between the different particles. So in that case, the Hamiltonian, collective Hamiltonian, can be written in terms of the total angular momentum operators. That is this omega jz, jx cross b, where b is the bath operator, plus hb. hb is the bath Hamiltonian. So this J alpha, these are the total angular momentum operators, which are just summation over this sigma r alpha. Sigma are the polymatrices. So now, in order to understand the dynamics of such a system, say like we have these systems, these particles in some arbitrary initial state, and once we couple to the baths, then it will be like a non-equilibrium state, and then it will go towards the equilibrium, that is try to thermalize with the bath or try to go to equilibrium with the bath. And the master equation of the dynamics can be found by this Born-Markov secular approximations, the standard technique that are used in open quantum system literature. And for the independent coupling for each this two-level system, and also it is valid for multi-level in many cases. So this can be written like this. This rho r dot, rho is the density matrix of the spin of the, say, Rth spin. It is given by some Lindblad superoperator D. acting on this rho, and this exponential minus beta omega, here I'm just taking h bar is equal to 1. This omega is of course the frequency of the spin, and the beta is the inverse temperature. So the D is given by this super operator. I will explain soon. So the main thing is, whether we talk about independent or collective, the master equation is very similar. Mathematically, it is almost identical. The only difference is this super operator here. In case of independent, it is a function of the polymatrices, local operators. And here, this super operator is a function of the total angular momentum operator J minus and J plus, where J plus minus are just summation over sigma r plus minus. So sigma r plus minus are the spin that flips the spin like a annihilation creation operators. So this J plus minus are annihilation creation in the collective basis. So this Lindblad super operator is given by this. So here O is either sigma r minus plus or J minus plus. So this is kind of this super operator. So one can study this kind of master equation and find what are the steady states, how they evolve, okay, for both collective as well as independent. And this collective angular momentum operators. So just to remind you, we have this total angular momentum operator J square, which is Jx square plus Jy square plus Jz square. And the eigenstates can be written in terms of these quantum numbers J and M, where J corresponds to the total angular momentum operator through this relation, eigenvalue relation. And M is like the magnetization along the Z direction, where Jz, that is the total angular momentum operator along Z direction, acting on this Jm gives Mjm. So this is our basic quantum mechanics. And this J plus minus, which are the annihilation creation operators I showed just in this master equation. This J plus minus, what it does is, when it acts on the state Jm, it just keeps the J, the total angular momentum, constant, but the spin, the magnetization along Z direction is increased by +1 or -1. And remember that this M is a total sum over all the spins. It is not of any singular spin, it is a collective thing. And this J and M satisfy this relation. So if there are n number of spins, say we are talking about, say here, even number of spins, in that case, this J is between 0 and n/2, and M goes between -J and +J. If there are odd number of spins, we'll just have a half here. But the basic thing remains the same. So the thing is, this J plus minus changes M without changing J. And this, so what it means is the collective master equation changes this Z direction momentum M without changing J, and initial distribution of J remains preserved. That is, a dissipative path because of collective coupling cannot change the J, the total angular momentum operator. It only changes the Z direction magnetization. So, and because of these different master equations, different kind of mathematics, so the steady states for independent and collective couplings are different. The steady states are the states we reach at, of course, infinite time, much long time. So let us take J is equal to n/2, the maximum possible J. The reason I am taking this is because it has been shown that the mean work is maximum in this limit. It is like, in this case, the mean work goes like n square. That I'll show in the next slides. So because of independent coupling, remember that each spin is coupled independently to the birth. So we are just getting a product state of individual qubits. The steady state is a product state because the spins are not talking to each other. So the steady state for independent coupling, n number of spins, is just given by this Gibbs state, which is direct product of n number of states. So for example, if say the high temperature limit, that is beta going to 0, say beta is the inverse temperature, the average spin magnetization of each spin should be 0. Because it is a maximum entropy or high temperature state. In case of collective coupling, of course, the spins are sharing excitation, so it is not a product state. In that case, this collective steady state is given by, remember, we are keeping J is equal to n/2, and the J value is constant. The the bath cannot change the value of J. So it immediately puts a restriction on what the states can be. So this steady state is not equal to the independent steady state. And in this case, for example, if say the high temperature limit, the beta goes to 0, the total sigma Z total M should be 0. So each spin can have non-zero, sigma average sigma Z, but the total thing should be 0. So this is a very different kind of steady states, even though the master equation is similar, but because this J is constant for collective, we get different steady states. So now how this, I'll talk about is how these different kind of steady states affect the fluctuations and the thermodynamic uncertainty relation. So this can be, one can make these quantum heat engines by using this collective or independent coupling. So as Aditi mentioned, like quantum heat engines are very similar to classical heat engines. Only difference is in classical heat engines, say one has a container of gas and there is a piston which is compressing and decompressing the gas. And it is coupled to a hot bath and a cold bath, and we are generating some converting heat to work following the laws of thermodynamics. So in case of quantum heat engines, it is very similar. Only difference is that instead of the container of gas, the classical thing, we are considering some quantum system like a spin or a harmonic oscillator or a many-body quantum system. So here I'll be talking about a Otto cycle, which is like a 4-stroke heat engine. It is given schematically by this. S is the entropy and omega is the frequency. So let us look at the 4 strokes. So for example, say in the first stroke, I am changing the frequency, increasing the frequency of the particle of the system in the A to B. That is classically, it is like a compressing the gas. That is so then when we reach B, then we couple it to a hot bath. So A to B is a unitary stroke. There is no coupling to any thermal bath. In B to C, we couple it to a heat bath and there is a heat flowing to the system. Then C to D, again, changing omega H to omega C, that is decreasing frequency, or equivalently, that is like increasing the volume by decompressing. And D to A, you're coupling it to a cold bath, so that part of the heat flows out to the cold bath. So the remaining QH minus QC, we get out as work. So this collective or independent coupling that I discussed in the previous slides that are relevant for B to C and D to A strokes. Okay? So we can couple the heat engines either collectively or independently in these 2 strokes. So this kind of heat engines have been experimentally realized in different setups like ion traps, NMR, NV centers in diamond. So these are just 2 references, but there are several other works. In the last few years, they have come up. So the question is that, how we can look at these fluctuations in this kind of heat engines. So the things that I'll be focusing on are the noise to signal ratio, that is the variance of W. W is the work output divided by the mean W square. It is the noise to signal ratio. So for the independent case, something that we have studied in just textbook statistical mechanics course, the variance goes as extensively in the system size. N is the system size. So, and the work output is, of course, there are N independent engines, say, and the N independent engines give just extensive work output. So the noise to signal ratio is 1 by N. So what it means is, like as we keep on increasing the system size, the reliability increases, because the noise to signal is decreasing as 1 by N. But the question is, what happens for collective coupling? In case we run the heat engine by collectively coupling to the baths with the system. So the mean work output of N single qubit independent engines, it goes as N, scales as N, which is obvious because there are independent engines. Now it was shown that for collective case, it can be shown that the mean work output of N qubit collective engine goes as N square. It was shown like in the references, I think in the next slides, in the last few years, that because of this collective coupling, the specific heat goes as N square, and so the work output under some regimes scales super extensively as n squared. So it is a much more advantageous to couple it collectively, at least in terms of mean work output. But the question is, which one is more reliable in terms of the noise to signal ratio? I mean, if we get much higher work output, but the variance is much larger, then it doesn't really make sense to use collective heat engines. So we'll be talking about this noise to signal ratio, and also I'll talk about this thermodynamic uncertainty relation, that is the noise to signal ratio multiplied by the entropy production. The significance of this I'll discuss in the next slides. So first, let us look at the noise to signal ratio. So the way technically we can find it is just find the probability distribution. So for example, there are 4 strokes. So for the unitary strokes, say the energy difference is this for 1 stroke. And by solving the Schrodinger or the von Neumann equation, we can find the probability, say from starting from the ground state going to the first excited state, for example, from this, say. And then when we couple to the hot bath, again, we can look at the probabilities, say from going to the ith energy state to the mth energy state. From the steady state, we can find this probability that is given by this PNBC, and then, sorry, Pi beta H. And then again, in the unitary stroke, we can again find using the Schrodinger equation, the von Neumann equation, we can find this probability that it goes from, say, the state I to the state J. And then again, we can find the probability of the that it is in goes to state J using this that it is sorry, that it starts from some certain state using this steady state probability. The point is we can actually find the probability for going from one state to another state, and then sum over all possible realizations to find the probability distribution of work and heat. And from that, we can find this characteristic function, and from the characteristic function, just by textbook result, one can find the different moments. Right? So the Q is the heat input, say, and W is the work output. So we can find the moments using this. So now we are going to do this. And once we do this, what we find is for independent engines, of course, the mean work output goes as N, scales as N, which is understandable. Variance is also goes as N, which is also a statistical mechanics tells us that, and the noise to signal ratio goes as 1 by N. But for collective engines, the mean goes as N square, which was already shown in these 2 papers. But what we found was that the variance also goes as N square. So the noise to signal ratio, which is variance by mean square, is actually going as 1 by N square. And this violates the standard textbook result that noise to signal ratio goes as 1 by N. So what it basically means is the noise to signal ratio of independent by collective is N. That is, collective engines are much more reliable, almost like N times more reliable than independent engines, where N is the system size. Yeah. So also numerically, we verified that for collective, this is the mean work output. The independent work is linear in N, the collective is N squared. Also the same for the variance, independent is linear in N and the variance is N squared. And the noise to signal ratios, it just goes as increases linearly with the system size. So what it means is, as we keep on increasing the system size, collective heat engines become much more reliable and also much more powerful compared to independent heat engines. So basically, now after we talk about this noise to signal ratio, as I said, it shows that the reliability is much more. Also, there is this quantification, there is thermodynamic uncertainty relation, which Bijoy introduced. So it also involves something called the entropy production, which basically says that how much entropy is produced because the bath is exchanging energy with the system. Now, if this entropy production, basically say it can be given in terms of the Carnot efficiency and the efficiency of the engine and work and temperature of the cold bath using this. So higher the entropy produced, it means that we are wasting heat. So the efficiency decreases. So as an example, if sigma is equal to 0, then it can be then sigma is equal to 0 means eta is equal to eta c. So it just means that the engine is operating at the maximum possible efficiency, Carnot efficiency. So just to remind you, Carnot efficiency is the 1 minus Tc by Th. It is the maximum efficiency that a engine powered by thermal baths can reach. Whether it is classical or quantum, it holds. So as the sigma increases, that is we are wasting heat, and so this efficiency decreases. So having a low sigma is beneficial because it indicates higher efficiency. So the problem is the noise to signal ratio. In our case, we can show that this goes as some function of these temperatures and the frequencies divided by sigma minus 1. So as we decrease noise to signal ratio, that is make it more reliable, the sigma increases. So there is a thermodynamic uncertainty relation which basically combines all both of them together and asks what is the lowest bound of these two quantities, noise to signal ratio multiplied by the entropy production. So in that case also what we find is that this blue is for the independent case, this brown is for the collective case, the dashed are the bounds. So in both cases, it can be shown that the thermodynamic uncertainty ratio is greater than 2 minus sigma. So for independent, it is sigma independent, for collective, it is sigma collective. So, and again to remind you, the lower this thing, the better the engine is. So for the independent, it is higher than the collective case. And it is the dashed is the bound. So in both cases, independent or collective, they are actually higher than the bound, which is of course consistent. But even in this case, the collective engines fares better than the independent case. So, and also as we increase the system size, it actually becomes better and better. But just to, I mean, it also means that we also keep on increasing the temperature. I'm not going into that, but basically, higher system size is actually makes engines better in case of collective coupling. So to conclude, collective heat engines have higher mean output work. That is, for independent, it output work scales extensively. For collective, it is super extensively. Same goes for variance. Variance for independent goes as n. For collective, it goes as n square. But what it means is, since the noise to signal is variance by mean squared, so the collective is much more reliable, actually n times more reliable than independent engines. And also the thermodynamic uncertainty ratio is lower for collective heat engines, which again says that collective is better than independent. So thank you.
So thank you, Victor. You have been amazingly punctual.
Thanks.
Right. So are there any questions? Yes, there is a hand raised. So please ask your question.
Victor, Bijoy here. So one question about this uncertainty. So I could see that you see the violation in this finite time version. So how do you have the lower limit? Like how low it goes? Do you have any?
Thermodynamic uncertainty is given by 2 minus sigma.
Yeah. So how low does it have any lower bound? So you certainly violate the bound 2.
Yes.
So does it go up to 0 even? Like it can?
So the sigma is given by this. So W collective should go as n squared. And the efficiency for collective and independent are same. So I would say sigma, as long as the temperature of the hot bath is high enough, the sigma should go as n squared. So
right. Okay. Thanks.
Any further questions? Okay, while people are thinking about it, I have a question actually. So the point is that when you are talking about collective performance versus individual heat engine performance, in terms of efficiencies and etc., what is it that, I mean, are you making any assumptions on how these collective engines are coupled? I mean, you know, what are the, where is this,
so this is the Hamiltonian.
Correct.
So coupling means, for example, say so here independent say they have different baths. Say, so I mean the crucial thing is that the bath cannot distinguish between the different systems particles. So that a single excitation from the bath can be shared by all the particles. So this can be, for example, happen if all the spins are equivalent. There is a kind of a translational symmetry, and there we have a single bath kind of.
Right. So basically, what you're essentially saying is that it's not possible to determine where the excitation has gone.
Exactly.
Essentially. But the
Right.
thing is that, so what is a quantum system where you would expect such a thing to happen? I mean, I can think of cavity systems, etc., where
Right.
definitely this stuff happens. But I mean, you know, and there's one more point that I wanted to this thing. So does it mean that you are more and more, by just putting a collective coupling to the bath, you're more and more going into the thermodynamic limit in this situation?
I mean, okay. So thermodynamic limit means, yeah. I mean, a large system size is equal to thermodynamic limit. If we want to say it like that, yes. But it is not the classical limit.
It's not the classical limit. Okay. Yeah. Okay, that's basically right. Any further questions? Right. If not, then we can conclude this talk, and thank you very much.
Thank you.
And let's move to the next talk, which is by Sumeru Hazra from TIFR. Sumeru?
Hello. Yeah. Can you hear me?
Yes. Yes.
Okay. And
absolutely.
the screen is also visible, right?
Absolutely.
So I'll enter the full screen mode.
Yeah. Perfect. You're good to go.
Sorry. Yeah. Okay.
Yes. Start.
Cool. Yeah. So good morning. I am Sumeru Hazra. I work on superconducting qubits at Tata Institute of Fundamental Research, Mumbai. So first of all, I'd like to thank the organizers for giving me this opportunity to present my work. And with that, I'd like to start my talk on extending qubit coupling beyond nearest neighbor using a new ring resonator-based coupler. So quantum computers theoretically are expected to outperform classical computers for a wide class of problems. For example, unsorted database search, quantum simulation, large prime factorization, and optimization problems. So the fundamental building block of quantum computers are qubits. So unlike a classical bit, which can only be in 0 or 1 state, a qubit can be in infinite superposition states spanned by the bases 0 and 1. So mathematically, the state of a qubit can be written by these parameters theta and phi, and geometrically it can be represented on a block sphere, as shown here, with the 2 poles representing the 0 and 1 state, and every point on the block sphere representing one unique superposition state. So there are several physical platforms to achieve a quantum processor. And the front runners are superconducting circuits, ion trap, silicon qubits, photonic qubits, and there are many more other platforms that that can make quantum processors. In our lab in TIFR, we work on superconducting qubits. Superconducting qubits offer several favorable features, such as tolerable interactions between qubits and also with the environment, and ease of fabrication, long coherence times, fast logic gates, both single qubits and multi-qubit gates, and finally, scalability. So superconducting circuits are basically nonlinear LC oscillators, where we replace the linear inductor with a nonlinear superconducting element known as a Josephson junction that serves as the nonlinear inductor. And then the potential is of a cosinusoidal form. And then the levels of this well are unequally spaced, allowing you to selectively address the first 2 levels. And typically this transition frequency is in microwave regime. So you can use microwave pulses to manipulate and measure the state of these qubits. One such most commonly used qubit design is known as trans 1, which is formed by capacitively shunting the Josephson junction with a large capacitor. Now, if you want to like couple multiple qubits, so one can do that either via direct capacitive coupling, or you can use what is known as a bus resonator, which is basically λ/2 resonators connecting 2 qubits, as shown here. So using a bus resonator basically offers you to couple qubits which are spatially further apart, and that is often useful in a processor design. Here is a like the same thing here represented in a 3D circuit quantum electrodynamics. So basically use a 3D waveguide cavity both for readout of the qubits and for the bus resonator coupling 2 qubits. So despite all the favorable features that superconducting circuits offer, it suffers from a major drawback that the coupling in superconducting architecture is limited to nearest neighbor only in most cases due to topological constants. So here is a standard layout of superconducting qubits in a planar geometry, and each of these circles representing a qubit, and these like bonds representing their connectivity. So now this affects the performance of a processor. For example, if you want to implement an algorithm and that requires you to implement a gate between two qubits which are not directly connected, this operation has to be implemented via several intermediate qubits as shown here, and that will lead to more number of operation for a given quantum gate. And since you are since you have finite coherence times for the qubits, this can lead to erroneous operation and give you a faulty outcome in a quantum algorithm. On the other hand, the competing platform of IonTrap, they have all-to-all connectivity, and that is often beneficial for a processor up to like 10 qubits, which don't have quantum error correction, and you want your algorithm to be implemented as quickly as possible. So the question we ask is whether we can increase the connectivity between qubits in a planar superconducting qubit network. So one way of achieving this is to couple several qubits at the antinodes of a bus resonator, as shown here. And this has been recently demonstrated up to 20 qubits by this group. But the drawback of this idea is basically now the coupling between the qubits are highly non-uniform. And also due to the proximity of the qubits here, it suffers from large microwave crosstalk. So can we come up with a design which don't suffer from this kind of drawbacks? So we propose to use a bus resonator, which is now in the form of a continuous ring resonator, and we couple the qubits to that resonator while keeping them distributed along the periphery of this resonator. We show that using this architecture, you can couple one qubit to most other qubits, achieving quasi all-to-all coupling. And since the qubits are now spatially further apart, they suffer from a low microwave crosstalk. Also, we analyzed and found out that the coupling between qubits is now more uniform across different pairs. So here is the physical implementation of this idea in 3D circuit QED architecture, where you can see that the ring resonator here is basically suspended on 3 sapphire chips placed underneath it. And here are the qubits, and these are the readout resonators to control and measure the state of the qubit in this architecture. So to understand the working principle of the ring resonator, so the working principle is based on 2-path interference. So now each qubit is now coupled to each other via 2 independent paths, and the interference of these 2 paths gives rise to the very unique coupling profile as shown here. So the fundamental mode of the ring resonator is kept at 3.1 gigahertz for this simulation, and we operate the qubit between the fundamental mode and the first harmonic of the ring resonator, and we can see as a function of relative angle and the frequency, the coupling has this profile. As I mentioned earlier, in our implementation, we have 12 qubits, which are specially further apart by an angular separation of 30 degrees. For that, the relevant angles are shown here using the vertical lines, which are at the integral multiple of 30 degrees, and which are separatedly plotted here in this plot. And you can see that at this special frequency, which is at the mean of the fundamental mode and the first harmonic, the coupling between qubit pairs are only, basically, they have only 2 different values for the connected pairs. So for 60 and 180 degrees, they show a larger coupling, and for 30, 90, and 150, the coupling is slightly lower. And the coupling between qubits, which are at 120 degrees apart, for example, this and this, so the destructive interference leads to 0 coupling between the 2. So now coming to experimental implementation of the same. So the cavity is now made in 4 parts as shown here. And then here is an image of partly assembled cavity. So this is the top part which closes the system and basically forms a whole cavity. And in this experiment, we have used only 4 qubits here, which were sufficient to sort of explore all possible angles in this geometry. For example, this qubit 9 and 2 are separated by 30 degrees, and 1 and 3 separated by 60 degrees, and so on and so forth. So now we move on to demonstrating experimentally the coupling between the two qubits. And for that, we perform two independent experiments. So first, we do an anti-crossing experiment by using a Stark shift on one of the qubits and bring them on resonance. And the gap between the gap shown here at the fully hybridized state is basically 2G, where G is the coupling between the qubits. We also implement another experiment, which is a conditional Ramsey experiment, and we use that to measure the cross-Kerr coupling between the qubits, and that is related to the Bayer exchange coupling. And we use these two experiments to sort of compare the interqubit coupling, and we compare it with the theoretical estimation of the same. And we find out that like they agree quite well for all these angles that we have in this geometry. We see that the 60 and 180 show higher coupling, and then the coupling for 30, 90, and 120 are roughly similar. The slight mismatch that we can see here is attributed to the asymmetry in the experimental system and some chip placement error. So now, so we also measure the crosstalk between the qubits, and we see that the crosstalk between qubit pairs is significantly lower than the state-of-the-art processors, and we attribute that to two different things. First, that 3D architecture provides you a better microwave isolation, so that now qubits are like they are in proper enclosure and they don't see other qubits. In addition to that, the spatial separation that you have between qubits also help to achieve this low value of crosstalk between them. So now we have shown that we can actually break the limitation of nearest neighbor coupling, and we can extend the coupling to far beyond nearest neighbor for up to 10 qubits. But how do we scale up this idea? So for that, we offer two different proposals. So the first strategy is to use a larger ring resonator itself. So for example, instead of using that 3.1 gigahertz ring resonator, one can use a ring resonator which is roughly 3 times in length, and that can accommodate thrice the number of qubits. However, like always on coupling for a large connected qubit network like this is not a desirable feature, because that will lead to unwanted and uncontrollable qubit crosstalk. By that mean I like each qubit is going to have some spurious coupling with other qubits, even if you don't want to do a multi-qubit gate. So for that, we propose to use a tunable coupler between each of these qubits and the ring resonator, so that you can now turn on the interaction only between the selected pairs while keeping the other qubits isolated from these two. With that integration, this is going to look something like that. And then we again numerically find the coupling profile, and we see that like every fourth qubit is not connected to this particular qubit, and the other qubits are connected to this one with only 2 different values shown by these red and blue dots here. And here is the numerically generated coupling plot as a function of frequency. However, the price you pay for going to a larger ring resonator is that now the variation as you move, variation of coupling as you move away from the special point is now faster. So the other way of scaling up is basically to use multiple ring resonators as shown here, and they are connected via a lambda by 2 section like this, and we can choose the impedance of this 2 sections such a way that like you can have uniform coupling. And as shown before, we can continue to use tunable couplers here, and we can then scale up this idea to several ring resonators connected like this, and we numerically estimate the coupling. And as before, like as a number of ring goes higher and higher, the variation of the coupling is going to go up. So that can be circumvented by using another like element in this lambda by 2 sections, that is a tunable coupler. So you can break the coupling here and effectively keep the effective length of this resonator smaller. So with that, I'd like to conclude. So we have introduced a novel coupler designed for getting long-range connectivity between qubits. We have shown numerically generated data for the coupling. and we have found decent agreement in the experiment. We have also demonstrated that they actually have a much lower crosstalk, microwave crosstalk compared to the other architectures, and we have discussed possible extensions. With that, I'd like to thank you for your attention, and I can take questions now.
Right, we are open for questions. Thank you, Sumeru. Are there any questions? Yes. I don't see who has raised the hand, but
hi, Sadiq.
Prasanna, yeah. Carry on, please.
Hi, yeah. So great talk, Sumeru. So I had a question. So with these 4 qubits, I guess that's the one that you've already experimented, right? So
yes.
That's the one. So could you also sort of make in some sense like state prepare into subradiant or superradiant states? Because I guess now you can couple. So it should be possible to make some interesting collective states, right?
You mean inducing many-body interaction, right? Like in the system.
Since this is a ring resonator, I'm assuming you can also get like all-to-all couplings, right?
Yeah.
So then you should be able to make one of these collective states, for instance, like the one that Victor was talking about.
Mm-hmm.
It should be possible to generate, right? So
I think it should be possible. Yeah. Yes.
So like super radiance, for example, like if you can sort of, so this already the spectral data looks like this should be able to do that. So have you tried that already?
I have not tried it, but it's a nice question. So we can actually try to sort of explore. We're actually looking for interesting problems that can be implemented in this kind of architecture. But yeah, I mean, we'll definitely keep this in mind.
So I think in solid state, I think there's so far with some quantum dots, there's been some demonstration of super radiance, but that's also not very controlled. So this is like really controlled. So you can actually turn on and off. Yeah, very cool. Yeah.
Thank you. Yeah.
Great. Are there any further questions? If not, then we can close the session here, and I will hand it over to Rajdeep, who needs to make some announcements. So please don't leave.
Thank you, Sadiq. First, let's just thank all the speakers in the session, and also Sadiq Rangwala, for chairing the session. Thanks to you, Sadiq, as well.
Thank the speakers, please. I'm sorry. Let's give them a big hand. And
let's give them a very, very big hand.
Yeah, it was a very nice session.
Yeah, just next session will start at 2:30. The rooms will open at 2:20, 10 minutes before the session starts. So please join us there at the links that have been provided to you in the program. And later on, there's a poster session from 5 p.m. But you can also go to the friends section anytime to look at any of the posters that you want. So I'll end here, and we will see you all again at